Thank you very much for your introduction. My name is Takeshi Sakai from Tokyo Tech, Japan, Tokyo, and I'm a research and R&D manager of QRIP, Quantum Metrology and Sensing Headquarters. Today, I'd like to talk about the diamond NV quantum sensor research in our QRIP project, especially wide range and accurate current sensor for EV battery monitor I will show. Okay, today I start at what is the QRIP and also a diamond imaging center as quantum sensor. And after that, targets in QRIP project I will show. That is first one is EV battery monitor, and the next is the sensor for biomeasurements. And after that, I'll show you the Quantum Innovation Hub, QRH I call, in Japan, and summarize my talk. Okay, this is the organization of QRIP Quantum Solid Sensor Flagship Project. QRIP is the biggest quantum technology research program supported by Japan government. MEX is the Ministry of Education, Culture, Sports Science and Technology. And in the QRIP, there are many of big projects, but as for the QRIP Quantum Solid Sensor project, this is started at 2018 and continued to the 2027, 10 years project. And members for the research and students, over 100 people included. And the total budget for this project is around 30 million euro. And this project is, directed by the Professor Arakawa, Tokyo University, and the representative researcher is Mutsuko Hatano, Tokyo Tech, and I myself is the R&D management leader for this project. And there are 3 layers of research included of this project. That is basic science and technology layer, and sensor system layer, also prototyping and application layer. In the basic science layer, we have members of this research. This is Sumitomo Electric for the synthesis of the diamond, for NV diamond. And also, this is the AIST group for the synthesis of the diamond by CVD. And in the application layer, we have 3 companies and 1 university research group. That is Denso, aiming to the application of MEG, and Hitachi want to measure the nerve cell by using the NV center probe. And also Yazaki is one of the big tier 1 maker that they want to monitor the battery for EV. And Tokyo Tech leading the sensor system development. That is a key for the whole integration of this research. Okay, what is diamond NV theta as a quantum sensor? You may know the NV center. That is a nitrogen vacancy pair of defect in diamond like this, nitrogen and vacancy. So we call the NV center. And this is a very, this shows a very strong photoluminescence when we irradiate a green light to the diamond like this. This is a green light and emits a very strong red photoluminescence. And this luminescence is affected the outer environmental magnetic field, electric field, and temperature and so on. And so we can use this kind of nature as sensors. And our target in QLEAP project. First is the energy electronics. In this field, we multi-scale and multi-modal. That means the current, temperature, electric field, sensing, implementation on power electronics and battery is aimed. And next field of the target is biomeasurements. In this field, magnetometrics for nerves, tissue, brains of small animals and humans are aimed. And also temperature measurement inside a single cell, as I talk later, will be aimed in this field. Next few slides, I'll show you the EV battery monitor results. This is the challenge and objective of the current monitoring for EVs. As we know, the state of charge management of the EV battery is very crucial to get a long driving distance. But right now, not a full charged current is not used to driving of the car. There are more than 10% margin is used for the safety. Why like this big margin is necessary? This is the WLTC mode current profile example. For the EV car, more than 100 amperes current sometimes we must measure, but the average current we need to measure is around 10 amperes. So we need a very small current precise measurement is necessary to know the accurate state of charge. But now most used current sensor such as Hall sensor is not so accurate because if we cover the more than 100 amperes range by using the Hall sensors, the accuracy of the sensor is around 1 ampere. That is very big. But if we achieve the 10 milliampere accuracy, covering the 100 or more amperes, we can reduce this margin less than 1%. So in this case, we extend the driving distance more than 10% or reduce the battery around 10%. So this is the NV sensor setup and the performance of the battery current monitor. In this sensor, this is a diamond chip with NV sensor. Is available from the Sumitomo Electric collaborator. That is attached to the optical fiber and irradiating the green laser from the behind. And so, like this strong photoluminescence is detected by this way. And the sensor is located to the battery bus bar on the both sides of the bus bar, like this. This is a bus bar. And bus bar's current generates some, so like this magnetic field. The up and bottom side of sensor detect this electric field, magnetic field. But, so by using this kind of location, we eliminate the outer common environmental magnetic noise. And this is the result from 10 milliamperes to the 1000 amperes. It shows a very linear response. And this is current accuracy from the 0 to the 10,000 amperes. All these ranges, the accuracy is less than 10 milliamperes at the very wide range of temperature. Here is the test performance test for the EV batteries. That is a high current measurement up to 1,000 amperes at a temperature ranging from minus 40 to 85 degrees. That is performed at the Yazaki Corporation. Okay, next is the bio measurements application. This is an example for the high resolution imaging of large cardiac current. In this case, small NV sensor is close to approach to the surface of the rat heart, and because of the sensor is very tiny, we can approach to the very close to the surface of the heart, so we can get a very high resolution magnetic field mapping that converts to the current flow mapping like this. Also, this is other example by using the tip type NV diamond sensors. In this case, NV sensor tip, the size is less than 1 micrometer in diameter, is made and put into the cells. And because of the cell tip is very small, tiny, the input inside to the cell is no problem, and to the inside to the outside. And any place of the inside of cell can be measured. And why like this measurement is important? The activity of the cell is measured by the temperature of the inside cell. So it's necessary to improve the success rate of the fertilization of the sensor. Okay, and this is a sensitivity improvement approach toward make of human. Features of NV sensors, that is wide dynamic range, room temperature operation, are quite attractive for biomagnetic applications such as make. But for this application, further improvement of sensitivity is strongly expected for these NV sensors. Very recently, we have just achieved the world's highest DC sensitivity of 9.4 picotesla per root hertz. This is the world record of this NV type sensor in the DC range. And in this case, the sensor, the output photoluminescence is sort of empowered by the like this mirror-like structure, and efficiency becomes very high. So lastly, I'll show you the Quantum Innovation Hub in Japan. Japan government formulated the quantum innovation strategy since 2020. According to the strategy, Japan's leading institutes and universities are organized as the Quantum Innovation Hubs, QIH we call. Originally, these 8 institutes and universities are included as a QIH, and Tokyo Institute of Technology, Tokyo Tech, are positioned as the quantum sensor hub. And very recently, there are 3 more institutes also included as a quantum innovation hub. And QIH and Japan government organized Quantum Innovation 2023. That is the 3rd International Symposium on Quantum Sensing Technology and Innovation in person in Tokyo next November. A topic of Quantum Innovation 2023 covers the latest achievements, trends, and needs including quantum computing, quantum sensing, quantum cryptography, and quantum communication. And I'm a co-chair of this quantum sensing track. And so this is a very nice conference. Please join to this conference. Now we open the registration system from on this URL. Please register this. Okay, summarize my talk. Diamond set is a very spin qubit that can be operated at room temperature and work as a variety of sensors for magnetism, temperature, and pressure. The QLEAP Quantum Solid Center project is developing sensors using Diamond Setter for energy electronics and biosensors. Okay, thank you very much for your attention.